One of the things that I want to tell is that it's really easy to get lost into big data applications if you don't have a really strong research question. And that's the thing, because there are so many data, so many software and everything, that if you don't really have like a really strong research question, I think it's almost impossible to really perform that. But so one of the things that I really think that's important is always to look at the theory behind, like read papers, think about, read textbooks, go to the field, talk to people. And then, so because of that, I'm showing some examples of big data applications focused on my background. I'm a biologist, but I was trained as medical entomologist. So I've been dealing with modeling of disease vectors in Brazil. And so those applications are for dealing with these ideas. So both examples that I've been working on are related to species distribution modeling. That's something that you can use for any given species. I've been using mostly with vector species, but essentially you can use with butterflies, amphibians, and anything. So it started with people thinking about where can I put a specific conservation unit? Think about a huge tropical rainforest such as Amazon or Atlantic forest. And then the idea was to go to museums or other biodiversity repositories and gather data, having several species from amphibians, butterflies, and everything, and then overlapping those mapping distribution and say, hey, this place is a really good place for building a new conservation unit. Let's talk to politicians. So because it's a map, politicians would look at that and be really convinced about it. So it started with those ideas, but of course it developed for other purposes as well. Oops, sorry. But basically, I mean, in terms of technical things, what you have to do is to, so you have on one side your point data representing georeferenced collections, and at the other side you have raster data representing your environmental variables, any variable you want. Of course, it's important to think on the theory that you are relying on. In this case, for any species distribution modeling, the niche theory is the theory that really supports the map, supports the modeling. So you have to observe that. And so if you correlate point data against raster data as abiotic factors, you will have this scenario here, which is the scenario of the fundamental niche. So you are modeling, you will have a map of the fundamental niche of the species. So you are just showing the physical constraints of the species into the environment. Of course, if you add more data and you add raster data representing biotic vectors, then you will go to this scenario in here, in which you will have the realized niche, which is, of course, refined, because you are going to have the area occupied for the species containing the physical constraints and the biological constraints. But then, of course, if you can add finally, which is really rare, actually I barely see this approach, but ideally would be the best thing to do. If you can add into your point data set idea of source and sink dynamics, so that is the meta population dynamics. There are several models that you can use to do it. So you have like your point data representing meta population structure, and you will have raster data representing abiotic and biotic factors. Then you go to that scenario here. This is the truly and real occupied area for the species. So this is the idea behind, the theory behind those species distribution modeling. Now, I want to just show some, of course you know, but I want to show some of the geospatial technologies that are used for those kind of modeling. The first thing is providing a map, producing a map, building a map with beautiful colors, of course, but important correct projections, because Earth, of course, has a shape in your map, has a different shape, so it has to use the correct projection. And then you can show anything you want, basically. Here we are showing in these more strong red colors correlation between vector-borne diseases and COVID in the first year of pandemic, just to show health services overload. And of course, we don't see that for West Nile in Texas, but we do see for dengue in Mexico, Chiapas, and as well in Panama and Brazil for dengue and malaria. And this is, I mean, this map for a politician or for other decision makers is a really strong way to show things for, I mean, for anything you want, actually. If you want to save people's lives, that's the way to do it. The other geospatial technology is remote sensing. Of course, you know that, right? So we have more than 500 satellites right now getting data from anywhere on the ground. And there are many things that you can do it. So here I'm showing a mosaic of RGB composite images. Any composite image is made of 3 bands, red, green, and blue. And when you combine those 3, you have a visible colorful range of the Earth in which you can identify places that have forest, pristine forest cover, but also places that have been deforested, right? And so you can do it over time. So the United States Geological Survey has this beautiful Landsat program that you can use data, historical data back to the 70s and do this historical evolution of deforestation in the Amazon, almost any place in the Amazon. I tell my students that if you don't fall in love with remote sensing, you really have no soul, and that's right. Come on, guys. Okay, so the next thing is about spatial analysis. I really love spatial analysis because they tell other stories. They allow you to test different hypotheses. And specifically for grad student, right? Yes. We really want to test cool and interesting hypotheses. And perhaps spatial analysis is also an interesting thing. An important thing is that when you do like a non-spatial regression, you have just one dimension, right? The dimension of your data, the dimension of your sampling units. But here, you will have 3 dimensions, right? You will have latitude, longitude, and also the dimension of your sampling units. And because of that, you can see different things. So here I'm comparing 2 different scenarios in where deforestation can act differently to affect malaria incidence. So in this place, it is reciprocally correlated, and here it's not reciprocally correlated. So here, I had the insight about malaria and deforestation being kind of a unimodal relationship from that analysis. And of course, you can still add a fourth component here, that is time. So you have opportunity to test spatial, temporal, and your data. Okay, so that's enough. Let's go to the next thing. So as I said, we do have some biodiversity repositories, but initially we started with museums, like natural museums at Washington, London, or New York, or Brazil, or University of São Paulo in Brazil. So those museums were the natural repositories for species distribution. And scientists that started working on those places started to digitalize data. So these data are now available online. I would say that the GBIF, Global Biodiversity Information Facility, would be the best place to look at those data. But I've been working a lot with people from Smithsonian. They have this vector map. So Smithsonian has this Walter Reed Biosystematics unit, and they had this vector map that has several data from mosquito distributions, ticks, sandflies, and much more things. So this is one of the products that I did with them. This is the fundamental niche for Aedes aegypti for the current time, right? Yeah, you see that aegypti is really a tropical species, clearly a tropical species, but they do reach the United States, like some temperate zones as well, where of course it can be a vector of arboriferosis, right? So yeah, vector map is really, really good. Okay, now finally we got into the specific big data application that I wanna show you. Then, so in Brazil we have this little guy here. He's a female of Anopheles diurnii. This is the dominant vector throughout the Amazon. But we still have other species vector. So the Amazon is composed mostly of tropical rainforests, but we have some areas that have a kind of different type of forest, more like a savanna, because we have drier parts of the Amazon that are replaced for this kind of savanna vegetation. And then there is one prediction, future prediction, saying that if the climate gets gets drier in the future, you may have a replacement of species. And there is one group of Anopheles called Obitarsis that can tolerate this drier scenario. So we were interested in studying this group, and this group is not only a group of one species, it's a species complex. So in Africa, we have the Gambi species complex, but in South America, we have Obitarsis species complex. And a complex of species is something that, for taxonomists, as I said, I was trained as a mosquito ecologist and taxonomist. So species that discovery is something that we are really interested in. And you can understand that species are just getting speciated as we talk, right? And we can look at this into species complex. So imagine getting a lot of specimens in the fields. You look at the females and they are very similar morphologically, but then you look at the larvae and you see differences. You look at the genetic differences, genetic targets, and you see differences. And then you come up with hypotheses about having complex species to be understood. And now, so compare these two plates here. This is a phylogenetic analysis with two plates, one of the plates. So all these species belong to the complex, but one plate inhabits areas above or north to the Amazon River, and the other plate to the south. So you have Albitarsis F to be described, Janconi in homage of the American scientist Jan Pond, Albitarsis I, all of them are inhabiting this area. And then plate 2, you have Marijuana, Albitarsis G, Albitarsis X, H, Dineorum, Orzilinetes, and Albitarsis, the original. And then the first thing that we do it is if those are different species, one of the biogeographical hypotheses that you can test is they must have different niche or different spatial distribution, because you can infer some allopatric speciation there. Because imagine a really dominant species like Albitarsis in the past, covering all the South American territory, and then having these glacial events, and then getting some subpopulation isolated, then you would have this allopatric speciation, and then finally this isolation could become reproductive isolation that would end into different species with different niche and therefore different spatial distribution. And that's what we got at the first analysis. So each one of them, of course, you see some overlapping, but most of them kind of have specific distribution. One of the important things here, as I will show you, we use it. So this is not the fundamental niche. This is the realized niche, because we use it both abiotic and biotic environmental data, right? As for the species that inhabit north of the Amazon River, I think one is here, and the others here and here. So you see the spatial distribution of them is much more different and related to northern parts than the others, right? Yeah, so you have some similarities, overlappings, but most of those distributions are pretty much different to each other. Another way to look at those differences is comparing this ecological fingerprint for the environmental variables that were used. So we used 29 environmental variables. Temperature, precipitation, hydrological soil. So these first four are abiotic variables. But then we had these landscape variables that represent potentially biological interactions like competition or predation. And then, yeah, so because of that, we can defend the idea that we have really realized a niche. And compare each fingerprint just for seeing which environmental variable is more important for each species. You also see that you have really different kind of requirements. So it's a way of looking. We can say that this may look like the niche of each of the species. And of course, at the end of the day, we want to talk about transmission. and how this can correlate with health. One of the bizarre things about species complex is, although they are very similar, the females look really much the same, and genetic is different, but not so different. The transmission pattern is really, really different. Like the pink bar represents the Opitarsis, the original species, is really a poor vector, right? But then you have other vector species in the same group that have more competence or more capacity, but comparing to what we have here, we have differences that can be really important for interventions and vector control. And as long as we don't understand that, it's really hard, because this can make a big confusion for control activities. Okay, now in the next example, I will talk about global distribution of Aedes species, and the idea wasn't to look at a species complex, because those are not species complex. But the idea was so the research question here was, would the distribution of these, or would the fundamental niche for these species change in future climate change? So this was the main motivation for this application. We have some scenarios of future climate change. So this graph shows challenges for adaptation at this axis, challenges for mitigation at this axis. And we have altogether the 5 likely scenarios. So the most optimistic ones is the SSP1, which says that we don't need to do anything. If we keep business as usual in the future, we don't need to adapt. We don't need to mitigate. So whatever. The most pessimistic one is SSP5, which means that we will keep business as usual, but then in the future we will have problem and we will have to mitigate, right? We also have the SSP4, which is the sustainability scenario, which means that we will have to adapt. We are aware that problems will arrive, we will have to adapt, right? Change many things, how we produce things, how we consume. And this, of course, has a challenge for adaptation. We still have SSP2, which would be intermediate challenges, right? And finally, we have the SSP3, which is the one that really has high challenges, because it represents the regional rivalry scenario, in which we will need to both have challenge for mitigation and challenge for adaptation. So we use this scenario for seeing changes in the global distribution of Aedes species. According to the vector map, this is the most updated point data from Aedes aegypti and Aedes albopictus in the world. And again, we see that in comparison, Aedes albopictus can be more like a temperate kind of species in comparison with Aedes aegypti, which occurs in southern of United States. But if you look at Europe, for instance, and compare to Aedes albopictus, really, really different. At the same time, in Brazil, Aedes aegypti is all over the place almost, but albopictus is more kind of a southern species in Brazil. Okay, so this is the point data. And then we correlated with climatic raster data. So only abiotic variables to obtain the fundamental niche for each of the species. So the difference was expected. So Egypti, so this is for the current time fundamental niche for Egypti and Albopictus. Now, what I want to show is the most important outcomes that we had, showing the differences that we would see for Aedes aegypti, which were, so we have here for the regional rivalry scenario, we have here 2040, 2060, 2008, and 2100, a decline of the probability of encountering the species in the Amazon. This is most likely because the Amazon will become drier. This is a really likely outcome. And of course, these species, even for these species, will be dry enough for that for these species to won't be there. Now, the other comparison that we did with Aedes albopictus was to see what would happen in the future with these species. And I mean, this species, of course, is already present in Europe, but what will likely happen if you compare those four future scenarios is that it will likely increase its distribution northwards. Of course, this species already is a problem for Mediterranean countries such as Spain and Italy. They do have some outbreaks of dengue nowadays, but they are observing as well that some dengue cases are occurring in France. So there was at least one case in France. And then it would be likely also to have, if the species expands northwards, to have more likely those outbreaks. So I think so the summary of my talk was that, so with these big data applications, we could study complexes of species in the Americas and also investigate future species distribution under climate change scenarios. And anyone can just do it, the same thing with other species, having, of course, better approaches or better models. One of the things that can be looked at to improve for improvements is explore demographic and urbanization models, and also consider alternative analytical methods. So that's all for now. Thank you very much.
I will start with the questions. How do you think that climate change, certainly we're going to see these geographic spread, but what do you think it's going to mean for areas of the tropics where it's just going to get hotter and hotter?
Well, yeah, I think that one of the outcomes will be not only with the hot part, but with the water availability. So Amazon, for instance, is really sensitive to water because, so for instance, in the area that we are working on, the soil is really, really poor. And then, of course, you have that huge forest because you have a huge amount of water that is under the soil. But as long as you lose that water is not for granted. I mean, you can lose that water depending of the dynamics of the climate. It depends on the rivers, but as long as you don't have too much rain and those water gets stuck in other places, in the wrong places, I think one of the outcomes is having different species invading the Amazon. So we have a huge savanna kind of biome that would invade Amazon easily. And then this would change the dynamics of the other species. So at least for the Amazon, I think this can be a likely outcome. As for the transmission of malaria, still, though this Albutarsis group has some species that can transmit under this scenario. So, I mean, transmission could still be possible.
So we see with Anomalous Gambia more and more evidence that it's adapting in real time to these changing population dynamics. Do you see that with Anomalous Darling? Is it as good at kind of mimicking behavior?
Well, we don't see. I think Darling, as long as it can stay on tropical rainforest, it goes well. But I don't see Darling, which is the dominant factor, invading. And I would say that a Brazilian savanna would get a sink for Darling population, and that's why it don't reach too much often. It can reach southern areas of Brazil, but it's clearly a sink for the dynamics of its population.
The last question, I'll open it up to the committee. So what is bigger, the United States or Brazil?
Oh, I think United States.
Okay. I was wondering. Other question?
Yeah, I had a question. I really liked like starting from the point of like looking at like your ideal SDN is able to take in these like abiotic factors, biotic factors, and also some of these like kind of population dynamics. And I was curious, like, what does data look like on like trying to take into account metapopulation dynamics, like where sources are, where sinks are? Like, what kind of data do you need to collect to incorporate that? And then what did it look like to incorporate that into your model?
Yeah, it's important to say that in ecology, there was this heated debate, what would be the best theory behind. So, niche theory versus neutral theory. And I really like the synthesis from by Soberon because it connects the two theories. And I think both are important for ecology. But having said this, I think there are some models that you can use for testing source and sink dynamics. But one of the things that you can, if you really can sample for quite a long time in the same localities, in which you can also collect data from environmental variables, then you can see from like a season or 2 seasons or more moments in where in that specific area you have lower than expected growth rates for that population, and this can be estimated with metapopulation models. On the other hand, in the source population, we wouldn't have never in any season any estimation of lower than expected growth population for that soil population. And then in your model, you would indicate that geographical area, that coordinate would represent with that all that environmental variables would represent the source, and this would give another weight how the model would calculate. So it would, of course, give more weight to those environmental variables. So computationally speaking, it's not so hard. I think that the hard part is going to the field and have those data. But if you go to the biodiversity repositories, it's harder, right? So, yeah.
It's kind of a related follow-up, like, so what's dispersal distance look like for a mosquito? That's kind of like a silly and naive question, but like, if we're thinking about like going from a source population to a sink population, like, how far are they traveling, or is it taking like multiple generations for them to like travel across them, or what does that look like?
No, it's a really good question. I would say that for a single generation would be something up to 1 kilometer, I would say.
And it's species dependent, so maybe cichlids now things don't cover more than like 100 acres in their life.
Really?
But yeah, I mean, that's the kind of normal estimates as good as they are, which is not. But yeah, and off lanes on the other hand, yeah, easily cover a kilometer.
But then you have the Sahel thing, right? Because the Sahel area, the desert, Africa, you have, they put this balloon, huge balloon, up to 200 kilometers in the Sahel area. And they would see that by wind, you would have species crossing from the Mediterranean seas to the sub-Saharan, or vice versa. You would have like infected species in West Africa traveling through the desert by wind to Mediterranean cities and infecting people. And this was really heated debate as well, if the transmission was locally or if the species would be dispersed. And yeah, and they proved that. So wind can be really important in certain situations. And the estimated wind distance traveled by those guys were
Yeah, it's like 10 or 15 kilometers, which I mean, it's huge, and they're traveling in the course of the night.
yes.
Yeah. If you had a good enough wind model, I wonder if you could almost do like directed. So like the idea of like distance is not, like, but if you get the idea of like where wind's blowing, the distance between, even if the Euclidean distance between two places is the same. If you're moving with the wind or against the wind, like connectivity might be like kind of different in terms of like just
Yeah, that's right. But then if you are studying Amazon, I would say that wind can be important, in the rivers. So in the rivers, you may have these effects, not into the forest. Deforestation also can makes the increase of many importance.
It's also really species specific, because the second the wind starts blowing on their ladies, it's just going high. Yeah.
You do have a question from the online audience.
Oh.
If you wanna pull up the chat, or I can read it to you, either
Okay,
works, and you have some compliments.
wow.
And so at the top, yeah. So the question is just what,
That's my mom.
yeah, I think.
That's my dad. I love that. Okay.
So there's a
sorry.
question from Dr.
Oh,
Baker,
sorry.
yeah,
Um,
that's me,
okay,
there we go.
thank you for everything. Thank you.
Yeah.
I would love to know how we could leverage these methods to examine the intersection of vectors, public health, disease surveillance, and climate change to influence policymaking. Yeah. I think we did it actually, but I would say that we would need to include urbanization effects onto these models, and of course, the way it's really hard to estimate the human behavior, but when we selected a specific scenario, the regional rivalry, kind of we selected a human behavior, right? And we are seeing that in Brazil with this right-wing extremism increasing, and also elsewhere here in the United States and in Europe, for instance. And that was, in fact, that was a choice for the modeling. But I would say that more than that, we should also include urbanization and perhaps more of control things inside the models. Yeah. Okay, thank you for your question. All right.
So I've got one.
Okay.
So, thinking of your SDM of 80s and 80s South Pictus, where you're kind of seeing as, time goes on in those different models of climate change, that movement, or I guess that transitional area in Brazil where it's becoming less and less environmentally suitable. How do you think kind of, because in one way, one part of this, you're going to have the environment changing, and you mentioned it's likely going to be getting drier or much more drier. But one thing that happens is as places get drier, is people store more water, right? Which is 80s habitat, right? How do you think those two things would kind of interplay across that? Like, how does that affect those predictions, I guess?
Yeah, I think that's a good question. Yeah, I would say that this would happen, and that would represent a human behavior towards that. We already see that in some parts of Brazil, in the northeast, that is drier, for instance. So that specific human behavior could be included in the model, as long as we could try to predict human behavior towards that. But I would say that on the other hand, I think Amazon, I mean, a humid Amazon is hard for people, but a dry Amazon would be impossible for humans. So that's another thing that we may think. We may turn areas into in hospital places too. So yeah, I don't know. It's just models.
Yeah, I know.
People.
Thank you so much, Dr. Gabriel. Fantastic. Thanks for giving a Big Data Health Science Center presentation. We appreciate it.
Thank you very much.